Hello and good afternoon. A special thank you for coming along here today. It's not only encouraging, it's confirming to see that you also see this subject as important. Just for a matter of interest, can we have a show of hands? Who have we got? Have we got architects? Architects here? Architect?
Come out the back.
Out the back there? You're an architect? Engineers?
Hey.
Good. Suppliers, as in building supplies? Very good. Thanks for coming along today. We're all in this together, so thank you. Without further ado, I'll introduce the speakers. We have a wealth of experience here from far and wide. First of all, we have Miss Janine Graves, Associate Director of Home Charlie. Could you just briefly introduce us, Janine?
Yeah, thanks for joining us today, everyone. I'm an architect of 20 years' experience in the UK and Australia, working across commercial, residential, mixed-use development, and hopefully today I can provide some insight into modern methods of construction and supporting yourselves in a way forward.
Thank you, Janine.
Immediate past president of Engineers Australia Society of Fire and Safety and Director of Basic Experts, Dr. Jonathan.
Well, thank you very much. Here from Melbourne, don't really know why, except that you're about to hear a really cool product that's going to make a difference, not just from a Creaky building viewpoint, but from a fire safety viewpoint. So really glad to be here to talk about fire.
Thank you, Jonathan. And Dr. Scott Menegon, President of Australia Earthquake Engineering Society, works in a joint university and industry capacity. Dr. Scott?
Thanks, Harlan. Yeah, so I guess my background briefly, I'm a structural engineer, and I kind of work in a bit of a unique role where I'm 50% at Swinburne University doing research work and 50% working in industry designing buildings.
Thank you, Scott. And Mr. Ali Bataghva, Director Engineering Design Certification and a Senior Lead Structural Engineer. Ali?
Hello everyone, this is Ali. I'm from Queensland, a structural engineer for 15 years and doing linkage and steel design mostly. So my background is linkage and steel design mostly. A structural engineer, 15 years experience. We are running a business engineering designer certifications in Queensland now. Yeah.
Thank you, Ali. Mr. Glen Pring, the AWCI Technical Committee Member, Director of Flexi Tracks and Tracks Metal Systems. Glen?
Hi guys, well good from coming. I've been in the industry now for about 34 years, from a carpenter, builder and a building inspector's perspective. Currently doing product development and research into the building industry across a holistic approach. So yeah.
Thank you, Glenn. Welcome everybody to this day. Our subject today is a solution of Creaky Towers. I'd like to change that to an NCC compliant solution to Creaky Towers. What would be a use of a solution if it wasn't compliant, if it didn't meet the standards or the code? To achieve a solution, firstly we need to identify the problem or the concern. So what is a Creaky Tower? I decided to Google it, and I feel very sorry for people that are involved. This problem is very well known across the globe. It's a problem it's gone viral, but together we can come up with a solution. Whether it's a builder, a contractor, an occupier, a tenant, we can only build with what we've got. So we're here to provide a solution. So what is the actual problem? It's the internal noise within the building. It's the walls and ceilings, the partitions, the waterproofing, the fire ceilings, the cupboards and any other things that are fixed to the walls and the ceiling, and they're cracking, it's moving, it's creaking. And probably the best way to explain it is to just play a couple of little brief recordings, just so that you actually know what we're talking about here. So this one is in Australia. This one here is in Dubai.
Working?
This one here is in America. So you know what we're referring to. So what causes this noise? You could put it quite simply, it's movement. It's unwanted movement within the lining system. So what causes the movement? Well, it's the structure, or you say the structural core of the building is designed to move. So as years have gone on, their structural cores of the buildings have developed with the development of higher and smaller footprints, and we got this aerial effect, so the buildings are swaying. They're designed to move. The external or the structural core is designed to move. And to date, it's been a industry practice to secure the internal lining system to the structure, which when it moves, it tears it apart. We get this cracking and this noise, this breaking of waterproofing and fire seals. That's what's causing this problem. So that's how I see it as the situation. Dr. Scott, what do you say? If you would have done some research on this in the university?
Yeah, so at Swinburne, we've been doing research and testing into this Creaky Towers for quite a number of years now. And I guess the first thing to say, just to kind of clarify any concerns, sorry, let me rephrase that. Sometimes when the residents of these buildings hear the creaking, they think, oh, the building's unsafe, there's a structural problem. But I guess the first thing to put out there is, we haven't seen one thing to suggest this is a structural problem. So, no one's kind of suggesting there's any structural problems with buildings, no one's suggesting they're unsafe. Everything that we've kind of looked at to date and researched is it's really a non-structural creaking noise of non-structural elements. So I think it's good just to kind of highlight that it's not a structural issue, there's no safety concern, even though to some people living in these buildings it can be perceived differently. So we've done, as I said, we've done quite a lot of testing at Swinburne because we have some unique three-dimensional testing facilities. And what we've found is a lot of conventional ways of building partition walls and ceilings is that under movement in the building, you can develop this creaking noise similar to what Harland's played in those sound clips. And we've actually been able to, I guess, reproduce the exact same sound that's been recorded by these residents in the laboratory. So that's always a good indicator that we're kind of on the right track to figuring out what's causing these issues. And then we've kind of been working with different suppliers over the years to come up with different solutions to try and address the creaking noise. And then I guess more recently, we've tested the system that InTexas has on display.
Yeah, good. So I guess one thing we need to look at is who is it affecting, or what is the effects of this problem? Well, we look firstly at the people. You've got the occupiers of the buildings. So you've got this terrifying noise, this annoyance, sleep deprivation. You've got mental health, discomfort, and most importantly, financial pressure. They've bought this unit, it's mortgaged, whatever, and it's devaluing because it's not got the comfort and what they expected. And then, of course, it affects the building owners, the developers, the property owners, the body corporates, insurance companies, the valuers, the banks, lawyers, it goes on and on and on. So then what about the effects of the building itself? The actual building itself is, when a building's built, it's plastered, it's waterproofing's done, the fire seals are done, building inspector comes in and inspects it and it's approved. But then shortly after, with a small amount of movement, all these things are cracking and coming apart. So the performance of the building has declined. And the unfortunate thing is that you don't realise this has actually failed until there's a catastrophe or a problem. So, Ali, from your point of view, you're designing projects, so what do you say about it?
Okay, first let's look at what's the creaking noise and why we have creaking noise in buildings. Basically, in basic term, when we apply wind loading to the buildings, tall, slender buildings, they move back and forth, they sway, so we have differential movement between top and bottom slab in each level. So this differential movement means the top slab can move with different rate comparing to bottom slab, or sometimes in different direction. So that can put walls and ceilings in bending, and that can cause the walls and ceilings rub against each other. So basically, creaking noise coming from vibration in structures I call walls and ceiling still a structure, even they are non-structural members of the building because they aren't part of a structure of the building, but they are still structural because they have to carry a load. So what happened is the different materials rub against each other, so that creates vibration depending on how rough is the surface and how tight they are connected or sitting on each other, basically. So when you push two components or material against each other, if they have a rough surface, you try to rub them against each other, you create vibration that creates creaking noise. You see this creaking noise probably a lot at the ceiling to wall junctions and at the wall intersections, wall corners, and anywhere two materials are rubbing against each other, or like when plasterboard is connected to a stud. When plasterboard is connected to a stud with a screw, we are pressing two materials against each other. So when you press materials against each other, and looking at the screws are like a spring connection, like an plasterboard and metal can rub against each other. That creates vibration and creaking, that annoying creaking noise, basically. So what's the complication for the structural engineers to design this is walls and ceilings must be supported for day-to-day loading, like internal wind pressure, shelf loading, and all of these different loadings. In same time, we have to detach the walls from the top, so we make sure, to some extent, that walls are not moving differently at the top, when you compare the movement to the bottom of the wall, which is the bottom slab. So that's the complication. We are trying to come up with a solution in the industry as a whole, and hopefully we can get somewhere with that. Yeah, that's it.
Thank you, Ali. Glenn, what do you say? You're right across manufacturing, regulating and technical, so I'm sure you'd have a lot in your mind.
Yeah, just in regards to what Ali said then, is just looking at, I suppose, the materials, different surfaces, how things are supposed to, accommodate your movement, what's pulling and pushing, how do we accommodate that along the lines of, aesthetics, looking at square set ceilings, the things that people want to have. How can we do, I suppose, a holistic approach in keeping the back of our mind with acoustics and also fire? How do we put all those together in, I suppose, one mix and come up with a system that's going to tick all the boxes? As Scott said before, we've been doing testing in many years, changing things, tweaking things to come up with a good solution. I think now we're pretty well, I suppose you could say, it's just about ticked all the boxes that's spot on, that hopefully going forward that we can get rid of this issue, and it can be a thing of the past. As I was saying, the buildings themselves at the core are great, they're perfect, they're really, really good. We just got to get that last little, I suppose you could say, the internals fixed, and then we'll be fine.
So is there a solution?
Well, going forward, obviously you can see what's been advertised today at the Intex stand, the Cubic 360 solution. It's very quiet and it comes up with 360 degrees of movement. So what it's doing is that all the movement of the building is actually accommodating from the bracket itself in the head track, which now we can look at the scenario where we can connect all the walls together and create virtually a box within inside the floor. So these floors are moving at different rates, what Ali says, but it's not actually tearing, it's not pulling tension on the materials to try and pull the materials and fight with each other. It's letting, like we call it the slip joint, it's letting it do what it needs to do, and everything underneath just stays where it's supposed to be, and there's no tension.
Just need to speak a little bit louder, Glenn.
So at the end of the day, there's a solution going forward, and architects, I suppose, can get on board in regards to changing the design now. We don't have to have certain things where they're sort of governed by certain things that they need to do with what's out there. Now, I suppose, what you world's your oyster at the end of the day.
So basically what you've done is you've accommodated the movement.
Correct.
So the movement between the structural core and the interior or the internal linings, you've accommodated it?
Correct.
So it's a bit like putting suspension into a car, is that right?
Spot on. Yep, spot on.
So we've had the buildings, the structural core have developed over times as buildings have got taller. Yep. That's been updated and regularly
correct.
It's been developed. Now what we're doing is bringing the plasterboard, which is something we've been doing pretty well the same for 50 years, we're bringing that up to date.
Correct.
Is that right?
Yep, spot on.
So from an architect point of view, Janine, what can you say to help us?
I think critically from a design perspective, we're obligated to meet certain regulations and standards, and the main impact of differential movement between internal skins and external substructures is that differential movement is causing some irritation to the most critical components of the building, whether that be thermal insulants, waterproofing, acoustic attenuation. So there are quite a few number of factors in play. We're all au fait with using conventional methods of construction. So any innovation that causes us to think outside the box, to mitigate any issues with movement internally for personal comfort within residential commercial buildings is a good outcome. I think modern methods of construction are leading the way, and any product on the market will be of interest to the industry.
Yeah. Very good. Thank you very much. What about you, Dr. Jonathan?
All right, how many of you have ever seen a crack in a plasterboard wall or ceiling? Raise your hand. Oh my God. How many of you have ever seen a fire test of a wall? All right. How did the test fail? From a crack, the same crack. All right. Well, oh my goodness. What is the issue? We have thermal differential expansion, etc. We have movement of buildings due to wind. We have movement of buildings due to seismic events. If your plasterboard cracks, you have weakened its fire resistance. Now, by the way, I got into the world of fire engineering back in the 70s. Sorry, I'm that old. Back in the 70s because of an earthquake in Managua, Nicaragua. I went there as a young graduate student to look at the effect of earthquakes. My background was structural engineering. And what did everyone talk about? They talked about the fires that happened afterwards and how the fires spread through fire-resistant walls. So we have an issue. If we can design a building so that we don't have that cracking, so if everything stays intact during a normal event, like a normal wind, and the walls stay the way they should, then, and we can have the same walls function that way in a seismic event, we have kept the fire resistance level where it should be. That's what's so exciting about what we're talking about today. We've got a way now, a means of construction, to avoid one of the big weaknesses we have in plasterboard when it comes to fire.
Very good. Well done. That was very well put. You got anything more to say, Janine?
We talk about integrity in building form. You know, from an architectural perspective, we are working within smaller footprints. So we've got, you know, small footprint, tall buildings. The higher we go, the more challenging the issue is starting to become. You know, the structure is the structure. We'll always get differential movement, so it's what we're doing with the internal skin that will make all the difference. Essentially, we've got an envelope within an envelope within an envelope, and that internal envelope needs to act independent. From an aesthetic perspective, obviously it provides comfort for residents and tenants. You know, the longer you're in a building, and we talk about residential apartments predominantly because the tenure there is longer than what you would have in a normal office environment. That is the most critical consideration. People are going to sleep and not being able to sleep because of movement. It's a neurological thing. It's, you know, it's a perception of safety and comfort within the home as well.
It's like what Jonathan was saying too in regards to the firewalls. You know, with the new system we look at now, given it the way we've changed things and tweaked things, you can actually fix the plasterboard and the starts off to the head and the bottom track, creating a rigid frame wall system so the strength capacity's gone through the roof. So we haven't got the plasterboard, I suppose, holding the studs. We've got the studs holding the plasterboard. So when it comes to the fire perspective, the loads aren't on the plasterboard. The plaster's just there to stop that fire travelling through the wall. The wall's there to do its thing, the plaster there just to stop the fire. So it's something to point out as well.
Very good. Scott or Ellie, any more to say before we open up for questions? Or?
Yeah, no, I don't know whatever questions.
Yep.
Fire away.
Good.
Take.
It's a lot to get your head around. It took me, as a self-professed expert, Glenn had to explain it to me 3 or 4 times till I finally got it. Because we think typically in 2 dimensions, so we have a slotted deflection head and a wall can go up and down. But if it starts having to do this, the sealant, you know, I've sold billions of kilometres of acrylic sealant that cracks all the time, and we get complaints about it, and people think you can throw firebat in there and it's going to fix it, but they still all crack and it affects the acoustics and the well-being of people. So this is a 3-dimensional problem. So if you think of out of plane, not up and down, then you get it. And it is the key point for me is that you're taking the head track off the concrete and hanging it, and that is the suspension system. So if that helps you understand it, because it's a lot to get your head around.
Almost like a deflection head.
It is. It's a suspension. It's a great way of putting it. Suspension for the inner frame, with the outer frame.
Yep, spot on.
So we've put basically like putting suspension into a car. Now the occupants are comfortable and safe.
Correct.
Any more questions? There's a few down here. Sorry.
A couple of concerns. Firstly, at the start of your presentation, we're non-compliant. Not non-compliant with the NCC.
Sorry, what was that?
We're non-compliant with the NCC. Which part of the NCC are we non-compliant with?
No, I said we're creating a compliance system. So basically it allows for the in-plane and outer-plane.
No, but your statement at the start was that currently we've got systems out there that are non-compliant with the NCC. At the moment, there is no, with what we're talking about creaking phenomenon here, there is actually no requirement in the NCC which puts it into that classification.
I think you said the system is compliant by memory, correct me if I'm wrong here, but I think you said the system we're talking about is compliant with the NCC?
Yeah.
I don't think you said anything about non-compliant, but...
No, but are you saying the other systems out there are non-compliant?
Oh, sorry, you'd have to speak to those manufacturers, I have no idea.
Well, I do,
Okay.
genuinely.
Sorry?
That I do, genuinely. As someone that's worked with this, for 7 years.
So what you're saying is, that the other systems you're talking about, they are or they aren't?
We believe they are.
Okay.
And I find it interesting that you're using that metaphor to state that this system is
That
better.
this system?
Your system is better.
No, I didn't say it was better.
Well, can I
Yeah.
for a comment? I think more where they're coming from is they're saying there's this issue. There's been this issue in residential buildings where people have heard creaking noise. Now, when you start to move away from standard construction, so right now we're building a certain way, whether it's compliant or not, that doesn't matter. But there is this issue of creaking. And so if a developer comes to you and says, oh, I want a solution to creaking, then whatever your solution is needs to be NCC compliant. So whatever solution you put on the table, needs to be tested, it needs to be thought through. So I guess, from my perspective, it's not so much about the current systems, it's if you're going to put something on the table that's different, then you've got to make sure you go through the process. You've got to do the testing and do all the associated work.
I do understand that, and as I said, I've been working on this scenario for multiplex for the last 7 years. As a builder, we've been one that's been addressing this, and we know the buildings. I work with Swinburne, I work with Rondo, I work with Studco. So I find it interesting that the format that this is being put is it's a significant problem across the board. It isn't as much as what you're saying. We know where it is lying as a builder and the end user and dealing with it from day to day. So I just want to put that at the table. It is a phenomenon which happens. There are a lot of things we can do, not just with the wall system, but with the ceiling systems to help mitigate that. And I think that's one thing that your system will help in addressing that.
Yeah, that's good. Yep, great.
We're not actually condemning any system that's out there. We're just saying that there is a problem, and together we can only build with what we've got. So we've tried to develop a system that allows us to take that to the next level. So we're in it together. There's no blame or pointing fingers here. No. It's basically a solution to try and help bring. We're in the internal wall lining system, so we're trying to bring that up to the current.
Thanks.
Very interesting product. Thanks for the presentation.
Speak up, can't you?
Thanks for the presentation and the panel. This is really good. I've just got a couple of questions. So the system, I'm trying to get my head around whether it's a solution to the squeaky stud problem or a solution to non-compliance in fire rating, or a little bit of both. So when you're talking about the fire rating and the crack, Dr. Jonathan, thanks for that. It was very clear. Are you saying that the product's only required for fire-rated walls for compliance to fire rating?
I'm not sure I understand your question, but look, compliance says that the design you install has to meet the furnace test. It doesn't say that 5 years from now, it still has to have the same fire rating. That's not what our building code says. So the compliance question, which you asked, is correct. What we're doing is, in traditional design, is fine. This is a way to avoid other problems that can occur later on in the life of a building. Now, we don't have a lot of earthquakes in Australia. The one we had a couple of years ago in Melbourne cost $5,000 damage to my apartment and cracking on fire-rated walls that we had to go fix. Most of the repairs required cutting out the plasterboard, because if you just do mud and paint, you don't solve the fire rating, right? Now, does that matter? Well, we didn't have a fire, it's sprinklered anyway, so maybe it didn't matter. The point is there's a system that's been designed to fix one problem, the creaking, noise creaking building problem, that also does really well with improving another situation and making something a little bit better. All right, so you get twice the bang for the buck is how I look at it.
Yeah, no, that's good. And if I can be cheeky and just one more. In terms of the outside of the movement issues that this helps with, what's its capacity in terms of restraining the loads that we're trying to restrain? So what a head track does is we obviously want to restrain the loads on that wall, those out of plane loads. What your system's trying to do is allow the wall to move. So it's a catch-22. So how does the system support the loads that we're trying to restrain, but yield under the loads that we're trying to allow?
That's a good one for you, Scott.
Okay. The wall has to take obviously internal pressure, shear loading, impact loading, and all of those. So at the end of the day, the key thing is the stiffness of that red bracket you see there, to be able to get the day-to-day loading on the walls, and to basically be okay, for lateral movement, for seismic, for example, for seismic be flexible, but for the loadings, day-to-day loadings, that is designed based on Australian standards. Exactly. The stiffness of that bracket is going to be designed that is okay to take that load as a reaction load, shear load of the start. The other thing is we are looking at some other aspects of the building. I don't know, Scott, do you want to, that can increase the capacity of the wall systems, or?
Yeah, well, I guess just to further highlight what Ali's saying is it kind of becomes this balancing point between the bracket needs to be stiff enough that when you have shelf loading or internal pressure, the wall doesn't move too much, but then it needs to be flexible enough to kind of relieve that pressure from interstory drift. So there does become this fine-tuning point in the middle. So, as a result, you do need to have that kind of fine-tuned to be that point in the middle. It's kind of stiff enough that the outer plane loading is okay, but then flexible enough that it doesn't put the loads from the interstory drift.
Well, at the end of the day, I just say that as well. Day-to-day loadings on the wall are much more important for us to look after, because that can happen day-to-day. Creaking noise can happen, I don't know, every few months. Probably Damien knows better than me, with the experience. But it can happen every few months or every few years. And again, there are lots of people that dealt with it before. But when it comes to seismic and creaking noise, that's the second priority for us that we are going to fix one day in the industry, or now with the system. We are going to look after fire. Day-to-day strength of the wall is the most important thing. So that's the priority in structural engineering design for us, and making the bracket flexible for that seismic or movement of the top slab to be able to flex a bit. That's the second priority, to make sure people are comfortable basically in the building.
It's got another question over there. We're sort of over time, but we'll get over time.
Dane's question, I guess, do you actually have design capacities for the bracket? So as I'm a structural engineer, just like Ali, I guess if we're going to design with it, we need to know a limit for it, so we're not exceeding a limit. So just to sort of, is there a design capacity that we can use for the bracket? Is that published or available?
We can't hear you.
Try and yell.
Sorry,
man.
just looking for design capacities for, so we can actually design with it. So if it's used on a job, we're going to need to know, well, what is the design limit so we don't exceed it. So.
Yeah, so we've done that testing at Swinburne, and that's going to be all. We're currently still in the process of putting the reports together, but that's something we've tested for and will be kind of, obviously made available to anyone who wants to spec the system. Because you're right, you need to know that information.
As a unit owner, do I have to gut the unit and start again, or can it be retrofitted?
Yeah, you can answer that one, Glenn.
Yeah, well, it could be, anything could be retrofitted at the end of the day. It depends on how far you want to, I suppose, take something back to a skeleton. Anything can be done there, yes.
So is it, basically from the head track down?
Yeah, you
it's
probably have
pretty
to
well
remove the top part of the wall, the rest of the wall the same, and then change the head detail out, connect it with the bracket,
Here's a
and then
question.
you'll be fine. So, yeah.
Excuse me. So, because I can see you have some pre-cut hole on the web of the top track. So, do you think that cut will affect or will reduce the buckling and the design capacity, for example, the shear capacity and the bending capacity of the top track? And how can you determine the capacity for the design, please?
Did anyone get that? Scott, did you hear
He's
that?
saying about the holes. He said, does it change anything with the track? I think that's what he's saying.
Sorry, it's just a bit hard to hear.
Yeah, sorry, let me say again.
Sorry, I missed the question.
So you have some pre-cut hole on the web of the top track. So do you think that one will reduce the design capacity of the top track?
The hole in the top
Yeah,
track.
so how can you determine the shear capacity and the bending capacity of the top track, please?
Yeah, so the top track has the holes cut out of it, so that will obviously affect the bending moment and shear capacity. When you look at 4600, the light gauge steel code, there's formulas in there where you can look at the reduced shear capacity for a hole cut out of it. So that's probably that will probably be the primary way of assessing it.
Yeah, in the AES 4600s, currently the DSM is not 100% available for many type of hole and with hole spacing as well. So with limited the hole spacing and the size of hole as well. So yeah, you should think about how to determine the design capacity for the top track.
I can't quite hear.
Yeah, it's about the hole spacing. About the hole spacing and how that affects the shear.
Oh, yeah. The hole spacing is, 150 centimeters? Yeah.
The checkouts.
Yeah, but the testing for shear capacity, is in the process with Swinburne University, and obviously we have hole spacing and hole diameter, and we can always look at AS 4600 as well. So that's right. We are considering, Swinburne is considering, or Intex probably, that's Intex system. Intex is considering the shear system, shear capacity and bending, but you are right. Cutting holes in the track can reduce the bending and shear capacity, but we still make sure it is okay for our purpose. Say a capacity of a member, say just for everyone else that is an engineer, might be say 2. If we are okay with 1, for our purpose we are still okay. But yes, capacity is reduced. Yeah.
You had a question?
Yep. All right.
This guy in the blue shirt over here has been dying to ask a question.
Get off now. Oh, there's more? Oh, cool. Let's speak over. Okay.
Thank you. I have a couple of questions. First, can you hear me? Yeah? Okay. For your system which you presented, what is the lifespan?
What was the span? What?
The lifespan.
Lifespan. Lifespan.
Yes.
Well, that's what it is, lifespan.
How do you work out the lifespan?
Well, I think the primary thing with the lifespan will come down to the performance of the tape, which is, I'll happily admit that's not my area of expertise. I'm a structural person.
Maybe do the life cycle of the fire tape time. Testing.
Look, it's a polyurethane tape, and it's a standard foam like we use in buildings all the time.
Yeah.
The question is, how will its fire properties behave 20 years from now?
Yeah.
All right, I can ask the same question about any other caulk that we're using. I don't know. I can tell you right now it's good. I can tell you from this is a standard product. It's probably fine 5 years from now. 20 years, I don't think we have the data. It's a new product. And I could be wrong, but I don't think we have 20 years worth of data. But we do know these kinds of products tend not to reduce their fire rating with time, right? They tend to be okay, but I have no data.
Okay, another question, is there any maintenance required during the period that the product is used?
I can't hear a word.
Sorry. Is there a maintenance required during this period for the product, for the bracket system, or
There's
we
no
haven't worked that
maintenance.
out yet?
What's that?
There's no maintenance. He's asking about maintenance.
No maintenance. No maintenance.
Nothing is required? No? Okay,
No.
because it's a steel product, no? It's a metal product, yeah? That bracket.
The bracket? No.
Polymer.
Polymer.
Polymer. Yeah.
And this is it's applicable for the interior walls or for the exterior walls?
Interior.
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 Only for the interior walls?
Interior. Correct. Correct.
Thank you. Thank you.
So the tape, if you go to the booth after this talk, you'll see how the tape fits in. It's in a concealed space. There's no light. It's just, up next to the slab.
G'day guys. Probably a question for the architect. I hadn't thought of it being for the architect, but now I'm looking at you guys. Energy efficiency, water vapor ingestion, I'll say. How much consideration goes into the interior fit out around movement at present for movement in the bathrooms, movements at the facade, with your finishes meeting the facades?
Not a whole lot.
Okay, so that we may actually be, say for example, pressure testing for wind at the start of a project, brand new building, great big tick, you've got fantastic performance, but no 5-year, 10-year.
No.
So there's no consideration for movement.
No. Like I mentioned earlier, a lot of what we do is conventional methods of construction. It's tried and tested, it's by the book. There are many products on the market, and we use all of them. We have suppliers in and out of our offices all the time, and all of them are on the same wavelength as the other. So for us, it's about preferences to clients, typology of building, but ultimately the installation methodology is identical.
So do the actual structural engineers who design the structure provide you with a serviceability movement limit and say, hey, this building's going to move this much in a 50, 25-year storm? Something that's 100% going to happen in its life generally, if we're going to have those sorts of... do you get values of 20 mil, 10 mil?
Oh, look, they'll tell us to put an extra expansion joint in.
Oh, okay. No worries.
Which just allows for that slight differential movement depending on the span of a space.
Yeah, no. And Jonathan, have you ever seen a fire test of a wall that's had any racking on it, any in-plane, any of this movement? Has anyone ever fire tested something that's been moved?
I've never seen one done. Remember, when we do the fire test, the wall is pristine. The fasteners are within a millimeter of where they're supposed to be, not like we actually build them. These are non-load-bearing walls. They've tested. They've had the one test that I've seen has a 2-hour rating, a -120/120 rating. All right, and the earlier question about the tape, for example, and its longevity, we don't ask that question about any of our other products. We just say if it passes the test, and we build in accordance with how we built the test, then it's okay. And it sort of may or may not be. I think most of the time we get lucky. A, fire's a rare event, and B, we obviously have a large factor of safety, or we'd have more losses. I mean, how many of you have gone and looked at fastener spacing and find that they're 2 or 3 times the separation they should be? That's normal. But our buildings don't fall down. Our plasterboard still seems to work in fires most of the time. All right, we're lucky. Most of the time.
Just a question over here. After an earthquake event, does the system need to be replaced? Or how do you keep it maintained and how do you check?
You probably... Mike?
Maybe I'll make a start and then you can throw some more comments. I mean, the bit that I really like about this system, and I kind of come at this from someone who's spent most of their years in research in earthquake engineering, is really its application in somewhere like New Zealand, where the version that we tested essentially could be pushed to 1% drift with no damage. Now, 1% serviceability drift in Australia is kind of like a meaningless performance objective, but over in New Zealand, they're designing buildings to undergo 1% drift for a serviceability earthquake. So being able to have a product that was shown to be able to withstand undergo 1% drift without damage, I think is quite novel. So I actually really quite like it from that perspective. But I'll happily admit I'm an earthquake person. So.
Well, from my point of view, this system works very well for seismic actions. No, you don't need to replace anything after seismic. With conventional system, you might see some visual plasterboard cracks and these kind of things. Saying that conventional system, well, walls and ceilings are designed for seismic as well, but visually, you might see some cracks with the current system after seismic event. If it gets, to 1% all the way or 1.5% drift. But with this system, the performance of this system for seismic I'm talking about here, for seismic is definitely better than conventional. And yeah, you don't need to replace anything. Even for conventional, it's a matter of repairing some cracks in plasterboard. So yeah, you get lesser probably visual failure with this system, I say. Yeah.
All right. We done?
There's one.
Okay, yeah. I was just wondering, is it the one clip and the one flexibility of that clip, or do you have multiple different ones? The reason I ask is, if we're trying to build in that resilience to make sure that fire-rated walls don't crack over the time life of that wall, we have different internal pressures in New South Wales to Queensland. So in Queensland, we're going to need a bracket that has more structural capacity than in New South Wales. If we take that same bracket and install it in New South Wales with lower internal pressures, the movement of that building might be such that it racks that wall anyway and cracks the plasterboard in the fire-rated wall, hence we're in the same boat. So do you have different flexibilities of product that are going to be coming out for different applications?
Well, I guess I can initially comment on the testing we did at Swinburne, and then maybe Ali can add to it. So the testing that we did at Swinburne was really looking at a 92 stud, and we did a series of different tests we had 4 different brackets we used. So I guess to answer your question, yes, there is different brackets with different stiffnesses. I think this will 100% need to be an engineered solution. So the solution that you develop for Brisbane could look different to the solution for Melbourne. I don't think it's just going to be cut and paste. But yeah, we've done the testing on a 92mm stud with a few different size brackets. Whether or not there's further development in the pipeline, I guess it's probably up to you guys to comment.
Well, I quickly add to that as well. Having different stiffness for bracket, it's a good idea actually, for different wind regions. Saying that if we go with one stiffness, you always can get the adequate performance of the wall based on the bracket spacing at the top as well. Do you put it every second start, every start, it adds to the stiffness of the wall. Obviously, these two things go against each other, creaking noise and day-to-day actions, so we have to look for both. Finding that sweet spot, always, it's a different, difficult thing, and it can be different for different wind regions, you're right. But that's a good idea to have different stiffness. I think we as Swinburne can look at it for different wind regions as well. So I say Glen should give you some either reward or something,
That was good, very good.
No worries, eh?
Yeah, thanks. We're out of time
Very good.
anyway, yeah.
Sorry?
No,
That's it.
That's it. We're all good. So if you'd want more information, just go across to our stand at the G8. And for the architects here, don't forget to register for your informal points, CPD points, or scan the barcode or the QR code there, or come across to the stand and we'll do some online or face-to-face formal points, CPD, for the architects. So, and thank you.
Thanks, guys.